Hi everybody, welcome to my class of image processing. This is Professor Chang of Bugyeong University, Korea. And this is really the last class of this semester. Today I'm going to talk about the object recognition following the previous class. And today I will explain the implementation of the object recognition following the example of the YOLO. Okay. So the object recognition, you already know about the recognition and of the object. And this is localizing and recognizing the object in an image. So look at this image, there are two objects, and one is dog and the other is person. If I ask you, then you will easily find the contour of these two objects. So this is the object recognition. Okay, so our algorithm need to know who or what is the object and where the object is. Okay, so to implement this, you need to download the dataset first. So you may go to this link and download the data. We have lots of training images, you can find it. Okay, and so there is some validation images as well, and there are also test images. Okay, so you go to Keras site and you can download it, but it takes lots of time because the size of this data is very big. So please take a rest and just download the link, and you need to take a rest for a while. For me, it takes about an hour, but it's up to you, your network condition. It could be longer or faster. Okay, and after you download it, you need to unzip the data. And unzipping the data also takes lots of time. For me, it takes about 2 or 3 hours. Okay, after finishing all of this, then you can create your new project in PyCharm. And so of course you can use other IDEs if you like. And for me, I'm familiar with the PyCharm, so I'm doing this. First of all, at first I tried to do this with the core app, but I gave it up because the data size is pretty big. So, but if you like, you may try if you have enough space in your Google account, then you can try it. Okay. So in my case, I installed TensorFlow and Pandas and Matplotlib library and some other libraries as well. So I will explain it later. And in my computer, CUDA 10.1 version is installed. So I installed TensorFlow GPU 2.3.0 because these two are matched. So if your CUDA version is different, then you have to install the different TensorFlow version. Or if you are not using the TensorFlow GPU, or just you are using TensorFlow direct CPU version, then also the versions could be different. So it's up to your system. So please check your internet websites and find the best versions of TensorFlow. Okay, I create the Python file, and then I think you already know about how to use this PyCharm, what your ID is, but just simply I want to make it sure you understand everything already. So this is your code window, and in the bottom you can see the console of Python. And if you click terminal here, then you can install additional library using pip. Okay. And when you download all the files that are downloaded already, then you will see these 4 files. Okay. Actually, we are not using all these files because training all the ImageNet files, images, it takes too much time, and it is difficult to develop all the programs and explain it in this short time of video clip. So I just in this class I just want to try to distinguish two classes of images and try to localize those objects. So anyway, if you open this text file, then you will see the text sort of the object and its names. So ID of this object is N01440764, and if an object is recognized in this number, then its name, the class name is Tinka. So it's kind of a fish, but I do not know much about the fishes anyway. So it has a total 1000 classes of images, and the explanation files are here. So all the training information and validation informations are stored in these two files. And if you look at this sample submission file, and then you will understand how to make your submission file to the Kaggle. Okay, let's skip this. And okay, you also can see the image files. I already told you that we are doing only two classes. So one is the Eskimo dog, husky, and we have 1,300 images for this. And another type of image is Leonberg, and this is, you also have 1,300 images of this. So one thing you have to know about this is there is some images without these dogs in this folder. So many of these images in this folder has Eskimo dog inside, but some images does not have Eskimo dog in those images, because in that case we have to say that there is no target object. You understand? So it is easy to say, okay, if we say there is two types of object. Okay, this image is about the Eskimo dog, and this is about the Leonberg. Okay, that is a little bit more easier. But if we have to say, okay, there is no dog we are looking for in this image. Okay, that makes the task more difficult. So I say this is two classes recognition problem, but actually it's more likely to classifying classifying the images into three classes. One is finding Eskimo dog, and the other is finding Leonberg, and the third is no target in the image. Okay. And let's see the image folder. Okay, this is the image folder. Let's see. Okay. Do we have? Let's go to the image. Okay, here I copied these two images only. You see, there are lots of dogs inside, and in some cases you will see that the dog we are looking for is not inside. The different dogs are only available in some cases. Okay, my computer becomes very slow from the last from yesterday. So, well, can you see the dogs inside? Okay, let's go to the another folder, and you will also see the other images of the dogs. Okay, so we have 1,300 images here as well. Okay. Okay, and let's move to the original image folder. Okay, this is the original image folder. The image folders are divided into three directories: train, test, and validation. And if you go to train, you will see lots of images inside, and lots of different objects in here. You see? Okay. And as I explained before, then we are going to check only the two images here. Okay. And if you go to the ONOT folder, then you also see that same two folders of the same names. Okay, here you will see the XML files. You see here N02109961 underbar 14. So this is the image name, and this is XML, so this has the information of the image. Okay, you see the file name here, and the image width, height, and depth are defined here. And you also see the object and another object, because there could be two objects or three objects even here could be exist in one file. Let's go to the okay, here there is information of bounding box, the BND box. Okay, 0,86, and the right bottom coordinate is 128,190. It is, if you look at this file image, okay, 9961 and 14, you will see what it means. Okay, let's go to the image here. 14 here. You see here, there is 3 dogs. You can see one dog here. Okay, another dog is here. Okay, another dog is just here as well. Okay, we have 3 dogs. 1, 2, 3. So there are 3 bounding boxes. So we are developing a model of deep learning, and this model should predict the 3 boxes from this image. That is the goal. Okay. Right. So this was it, and then let's try to write some codes. I already wrote many codes, many lines of code here. Okay. So from now I will explain the code. Well, this is it, not that important, and I will delete this. Right. Okay, please ignore the code above. These are just the importing NumPy, and these two import my functions and deep learning is loading the functions which I wrote in my different files. Okay. So please ignore this. And let's move to this. Okay, in these 3 lines, I defined the folder names. Here is the XML folder, which has the information of the image, and the second is the image root folder, and the third is the image resized folder. Here, original image size is very different each by each, you will see the size of the image are all different. In most case, width of the images are 500 pixels, or sometimes height of the pixel is 500, and sometimes lower width or height are 500. So some cases, okay, this is well, yeah. If you look at carefully, then you will see the different size of images. So we have to resize these images to put these files into our deep learning model to train the model. Okay, so how to resize? We are going to resize that into 256. Okay. It's up to you in many cases, especially in YOLO. 227 was used. So but it is really up to you then, 256 or 227, 2047, it doesn't matter actually. So it's just up to you, and maybe for YOLO case, they tried many different sizes and their final selection was 227, and which was, I expect that was the best, but it could be different for us, so you don't need to follow the size of the image from the beginning. So maybe later you start from here, and then okay, you may try in many cases, and okay, then you will find the best case, then that is good. And another information here is any info per cell. This is the cell information. Okay. If you already watched my video of YOLO, then you will understand what this information is. The first bit variable explains whether the object is here or not, and then the second is the center, and the second and third variables explains the mean the xy coordinates of the center of the object, and width and height are the width and heights of the bounding box. So we have 5 information for one cell. So this is one box information. So here we assume that there is only one single box in a cell. That's our assumption, and which makes the problem more easy. And then, okay, let's start reading the XML information. Okay, let's close this. And this function is reading the XML files from the XML root folder, and then it detects the class names, box positions, XML images, image names in XML, and image names in XML ID to dict. So this, I explained this into this slide. Okay, dict class name to ID variable means like this. Okay, class name is this, and the ID, this is string ID, and I say this is just ID is 0, and for ID class ID 1 is means the object of n blah 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 29. I'm doing this because there are two informations here. One is the image information, image data itself. We have 1,300 information, and in XML files we do not have all the 1300 images, because there are some images do not without the object. So you will see there is only 977 images information, object information, and which means the other 23 images does not have the object we are looking for. Okay, so class names. The first class name is Eskimo Dog Husky, and second class name is Leonberg. And the another variable is dig image names to image IDs. So I say this is dig because this variable is defined as declared as a dictionary. Okay. When this dictionary has the key of this dictionary is image name, and value is image IDs. So if you put the image name for this dictionary, and you will get the image ID. The other variable here is image names to XML ID dig. So here, please understand that variable names are pretty ambiguous. Just I had to fix these variable names, but just I was too tired after developing all this. So, so this variable is denoting the image name, matching the image name to XML ID, because number of the XML information and image information doesn't match it, so we have to find the matching. We have to match this. Okay, image name, XML ID, image name, XML ID. Okay, so with this variable, you are easily find the information of an image. And please look at this another variable, obj box positions. So this variable has the information of object boxes for an XML file IDs. Okay, this is a list, and there are another list inside of the list. Okay, because there could be more than one bounding boxes for one file, one image file. So the data structure becomes like this, a little bit complicated. So each bounding box information, it has the name of the object, the string ID of the object, and the bounding box information, XY coordinates of the left top and the XY coordinates of the right bottom. So if the image has the object information of more than one, then it has the information of the boxes are stored as a list form. And this file, image names in XML, is the matching the XML file ID to the image information. So please check the previous dictionary here, image names to XML ID dig. So this is the dictionary to find the image XML ID from the image name, and this variable here is finding the XML ID to image name. So this is vice versa. Okay, then let's go back to the code. Then you will see that all the informations are stored here. So if you look at the functions here, you will see the codes inside, get image information from the file. So this is parsing the XML file, so it's not that complicated, but you will see, you will understand the read XML files. Let's go. It's not that complicated, a little bit long, but this is just a parsing all the informations. Yeah. So if you can just type all these codes directly, or not class names, okay, or you may ask me if you need this code. Okay. Oh, well, this code is not that public, but this is just open for those who listen to my class, if you like. Right, then let's to the main pie. Okay, then you will read, after running all these codes, then you will see the names and informations. Let's try to run. Okay, run. Okay, it's running. Okay, now this is loading the TensorFlow GPU and still running. Okay, and let me explain why this is running. And the next thing you have to do is resize the image. Which the reason why we have to resize is I already explained. So I gave the information of the folders of original image and the resized image to save, and then I will give the information how to resize the size of the resized image. Here this is a 256, and the last one here is not that important. This is, I set it true, but it should be false at first. I set it true because I already resized and just I want to get all the informations only. Here, if you go to the resize this function, then resizing function, okay, is like this. It just read all the images and convert it to the size of what we want and resize. Here, when we are resizing all these images, we have to keep the information of original image and the ratio of the image, because we have to. So I'm returning here the information of the resizing. This is necessary because we have to correct the information of bounding boxes, because the bounding box was defined from the original image size. So when the image size is changed, then this bounding box position and size should be changed as well. You understand? Okay. So here the bit B get resizing information only. If this is false, then this function really resize and save the resized image somewhere. And if this is true, then it will not really resize and do not save the resized image, but just keeping the informations. If you are running these functions several times, then you don't need to resize and save the image again and again. We already have the resized image, so that's why I'm putting this bit here. So after running this, you will have these two images. So if you go into this folder, then you will see all the images that I resized into 256 by 256, and the borders are black. Okay. So because I already have all the resized image, then I will set this bit as true. Then I will run the code. After running this, okay, it does not take that much time. I wish. And let's check. After resizing all these images, then what we have to do next is match file to file numbers. So this is something I explained it already. The image name to image IDs is this image name to image ID. So this, so making this variable. Okay, so let's get it. Then we have to correct box information with the resizing information, because box information now is just for the original image, and now we need to convert it for the resized image. Okay, so there is some problem, so I restarted the PyCharm, and now everything is seems to be well. So here I run all the programs until the line 13. So if you check the variable, then you will see the dictionary inside. So here, if you check the image names, put the image names, then you will see the ID, image ID directly. Okay. Then we have to update the box information from the resizing information. Okay, so this is a function to get to correct the box positions from the resizing information. And let's check if everything is well. So here there is some code at the bottom to check whether everything is going well or not. So this is the code to get the image file. So this line 69 is get image information from a file ID. So if I put file ID, if this is 555, then, and also give the resizing information, then it will draw the image. It will get the image file, file path, and the box positions of the image. Then if I give this information to this function, draw image with the object boxes, then it will draw the image with boxes. Okay, let's try to run here. Okay. Alright, you will see file number 555 is this image, and the bounding box is displayed here. So please do not misunderstand that this is not the trained output, but this is just the pre-defined the information of about the image in the XML. If you are interested in the other files, then just change the name, and you we'll see. So this file number 556 does not have the target object. This is not the target object, so there's no bounding box here. If you go to other image, then you will see the other result. Okay, the Eskimo dog is laying down on a sofa. Okay. Right. So you checked that the image is resized and the bounding box are resized together with the image. So now, until now, everything seems to be going well. Okay, and we finished it until here, and then now we can generate the target data. So here you need to understand the YOLO inside. So target data is looks like this. So this is not just directly estimating or predicting the bounding box, all the bounding boxes in the image, but it divides the output, it divides the region of the image. Then each cell, we want to check each cell has the center of a bounding box or not. And if there is a bounding box center in the image, in this subcell, then it also estimates the width and height of the object. So it is just like this table. So there are many informations. Here there are 3 classes, girl, dog, cat, and then there are 5 informations. First, whether object exists or not in the cell, and x and y coordinates and width and height information. Here you have to note that this x and y information is the relative coordinates from the center of the cell, each cell, and width and height is just width and height. And girl, dog, cat, these 3 informations are the one hot encoded data of the class. Okay, so this is a set of information. Let's see, this is a set of information, and then this is converted into the one-dimensional array. So if the image is divided into 9 cells, then the number of output node is going to be 9 multiplied by 8, then it's going to be 72 if the number of classes is 3. In our case, the class, we are using the class only two types of class, so it's going to be not 72 but 63 if we are dividing the image into 9 cells. But here in our course, we are dividing the image into the 25 cells, 5 by 5. So it's going to be different. Okay. Let's go back to the code then. Okay, then here we can run the code. Okay, number of cells are going to be 5 by 5, and then we are generating outputs from the data. So this function is inside of here, my functions. This is the code of generating the outputs, the targets. So this function looks like a bit complicated, but well, if you try to understand this function, then it's not that difficult if you understood the inside of YOLO. So output y is set to 0 with the size of an image file, number of image files, and number of cells multiplied by the information per cells. So here, information per cell, the variable, this variable is only 5, and this is the number of class. So if you look at my slide, then you will see there are 5 information, basic information per cell, and there are 3 information for the category, the class. So here in our code we have only 2 class, so it's going to be 5 plus 2. So if you move back to the code, where's code? Okay, here. So this is going to be 5 plus 2. So the output size is going to be like this. Okay, then for all the image files, we are checking for all the image files, we are making the outputs, the target outputs. So first we get the information of the file from the file number, and we get the file path and the box informations. So there could be no box for a cell. If there is no object center in the box, in the cell, then it's going to be skipped, and we can just move to the next file. If there is a box, then we find a box for all the box one by one, and we check the object ID and the center of the box. Then if the center of the box is calculated, then we also calculated the position of the center in the cell. So which cell includes the center of the box, we can know with the simple calculation here. Then also we can calculate the center position of the cell. This is necessary because we are using the relative coordinate for the box position here. So position, this POS here is assigned of the value y cell multiplied by n cell width, and x cell and multiplied by information cell number of information cells. As you know, this is 5 and this is 2, so it's going to be 7. So, and this position is going to be this multiplied by the cell position. Here, we know the cell coordinates, x cell and y cell. So if this coordinate is 2, 1, x cell is 2 and y cell is 1, which means that x cell is 2, and which means it's going to be x cell 0, 1, 2. This is 2 x cell. And y cell is, if y cell is 1, then 0, 1. So y cell is going to be here. So if it is 2, 1, then it's going to be, it will indicate the cell number 6. Okay. Actually, I wish you understood with this explanation. Okay, this is the position. So this position, this POS indicates the cell number. You understand? Okay. Cell number, and this here is sorry, this is not cell number. This is the cell number, right? Yeah, this is the cell number, and this cell number is multiplied by the number of information in the cell. So, which means the this POS means the array position. Here, if the box is inside of the number 6, cell number 6, then we need to know which position, the position of the cell, or all the informations in the 1D array box. So here we multiply by this. This is number 5 actually. This is because the cell number here is indicated from the 1 to 9, but actually in the course it is going to be 0 to 8. So this is going to be number 5. Okay, 4, 3, 0. Okay, so sure, in that way. So if this is for number 5, then when you multiply by 7, the number of information in the cell, then this will indicate the starting position of the box in this 1D array. So this may be indicated here or here. It could be here, or it could be here. So it's up to the position of the box. Okay, here, if the position is here, number 6, then in the code, the number of the cell is going to be 5, so if it's multiplied by 7, then 1, 2, okay, this is 0, 1, 2, 3, 4, 5, okay, here is going to be result of the POS, variable POS. Okay, here, so we get the position of the cell information, starting position of the output. So then we can modify all the information, we can put the information. So for the information of the cell, or the box for the cell is going to be like this. So PO starting from POS and POS plus and info per cell. And the information is going to be like this. The first one, number 1 here is this means that there is an object. And this is going to be the center coordinates, relative center coordinates of the box. You see the X center here is the position of the center position of the box. But here, this is the absolute value, and we are going to change into the relative value by subtracting this. Okay, then we are having the center, relative center coordinates from here, and then we can also get the width and height by subtracting two values. Okay, then this is the last, the class information. The class information is set to 0 for all, basically, because we set all the variables or the arrays as set to 0. And here we just set 1 for the object ID. So if the object ID is 0, then the first position is going to be set to 1, and then the second position is going to be 0. Okay, then let's move to the main code. We can have the target data. Okay, I already run it. And then next thing you need to do is normalizing the data. Because the values here is not shoot for the deep learning, because this number is too big. Generally, all the inputs and outputs should be between, it's better to be between 0 to 1. Okay, in some special case, it could be it could be bigger than 1, or it could be smaller than 0. It could be negative, but in the most cases, it is very general to normalize all the variables with the value of between 0 to 1. So we are normalizing it. When you are normalizing it, all the data, you have to be careful, because there are lots of zeros. Because there are many cells without the object information. So in that case, all the informations here are 0. So normalizing is not necessary, and it is not possible. So to avoid that case, so in the normalize function here is normalizing with the maximum and minimum value. But we are not dividing just y max by y min, but I used the max function here, so it may not divide the max minus means if this value is smaller than 1. Okay. In most cases, this is going to be 0. So if you are not putting this, then the normalized values are going to be problems, because we cannot divide something with 0. There are you will see lots of warnings, right? Then we have prepared the output. This output, you can print it, and you will see there are lots of zeros, but there are some ones, and also there are some values. Let's check. Okay, so this is the first images output, target output. You see there are some informations here. See, this is the value is 1 and 0 point something something, and then like that. Okay, then let's move to the next one. Now it's time for preparing the inputs. You may read all the images, resize the images, and you need to expand the dimensions. Okay, first we may read resized images using this function, and it takes time because there are more than 2,000 images, and you need, when you are reading all this, then you will need also lots of image space, memory spaces as well. So if you do not have much memories in your computer, then this may cause a problem. So in that case, you should work with the other way, not reading all the images once, but you are reading small by small and train small by small. So well, there are some classes in the Keras for those to support those cases, because for example, when you try to train all the images in ImageNet, then it's going to be impossible to load all the images at once. So you have to read all the images small by small at the case. Okay, now the X shape the X. The shape of X is just like this. So there are 2,600 images. Image size is like this, and the number of channels of the image is 3. And because we are going to use the convolutional neural network, this image size should be changed. So one additional axis is necessary at the end, so we change like this. So shape is going to be like this. Okay, then what we have to do now is deep learning. Okay, so I developed a neural network model just like this. Okay, similar to the VGNet, but it is more simple because we are just dealing with 2 classes. Okay, let's read the model. Okay, reading, it takes time. Okay, and then we are going to compile it. I used the mean square error and optimizer of Adam. Then let's start the training. Okay, I set the epoch 50, so it will say takes a little more time. As you see the training loss here, and also you will see the validation loss as well. It is slow. Okay, so also finishing the first epoch. Okay. Okay, you will see the loss and the validation loss, the differences. Now the validation loss is a lot lower than the training loss, but we just can ignore it. And it takes time, so let's skip the time. Okay, so the training has been finished. The final loss, training loss is 0.0025 and the validation loss is 0.0090. And frankly speaking, I have found some errors in my program, so I checked it and I modified the previous program, which I explained to you. That is the normalization function. Normalized data function has been modified a little bit. Before I normalized it channel by channel, and now I found that it's not meaningful, so I calculated the minimum number for all the coordinates values and minimum and maximum number of all the coordinates values, and also I calculated the minimum width and height and the maximum width and height for all the cells, and then I normalized the data with these values. Okay, that is the main difference which I modified it. And okay, because the training has been finished, so we can check the history. So this function through history is developed by me. It is a very short function, and this draws the loss changes according to the epoch. So you see the error drops, the loss dropped dramatically at the beginning, and also there is a significant drop between the epoch 25 to 35. But of course you can see that validation loss does not decrease but increased. So we can say there is some kind of overfitting here. So anyway, let's move back to the course, and because the training job has been finished, now we can test. We have to test after dividing the training and test data. But here, our purpose, our goal is not finishing this job, but just showing you that this is possible. I did not divide the training and test file, but all the data are mixed here, and we may try to predict this data using the trained model. Okay. This is the Keras function, and then we get this result. This is O. This is a pretty complicated number. Then we need to denormalize this output because all the values of the output are the normalized position and the normalized width and height. Okay, then I run it. The function, the normalized output, is the opposite direction of the normalizing. Here you see this is normalizing function, and the dim normalizing is using the min-max information and then calculate a new values. Okay, then after finishing the denormalization, we need to convert the relative coordinates to the absolute coordinates. So this is vice versa. So at the beginning we had to convert the absolute coordinates into the relative coordinates to put the data into the deep learning model. Now we are converting the normalized and relative coordinates of the output into the absolute values, denormalized absolute values. Okay, so here we get the absolute values. The inside of the absolute boxes is very simple. Here, so you see it. So there are many informations in output. So we check one by one and reconvert it. So convert back to the absolute coordinate by adding the center information, certain center coordinates of the cell. Okay, so then we get the absolute value. Then we utilize this function, get image information from file ID. So we just try to predict to 1 to 9. Then we run this function. Then we get the file image of this. This is the file path, and we also get the box position. Okay. This is not the predicted value, which you have to understand that this was the target value. So this is the answer. So how our answer is? Let's check our answer. Okay. I developed a new function, draw image with output. I give the parameters of the image file path and output, and cell width, cell height, and information cells and class names, and this is the threshold. So because our model, our network predict all the boxes, one boxes for each cell. So if we have 25 boxes, so our model predict 25 boxes, but not all the boxes are having the object information. The first value of the box is showing that whether there is an object or not in the box, so in the cell. So we have to check that value. Then we say that is the possibility to being a value, having an object inside of the cell. So here just I set the threshold very low, 0.1. So if the value possibility to having an object in the cell is bigger than 0.1, then it will draw the box. Okay, then let's check. Okay, so this is expected as the Leonberg 0.99, so 99%. This model says this is Leonberg, but as you see, the box here is not that clear. So but actually this dog has around this kind of big shape here, but it is expected that only this size. Okay, then let's move on to the first file. Okay, in that case, the box is not that bad. Okay, so it estimated that this is the husky, Eskimo dog. Okay, box is not bad. There's a little bit bigger here, but it's okay. So another box, let's say, okay, right, so there's another box. It says this is Eskimo dog husky, 100%. Okay, so okay, not bad, right? So it should, the answer was around here. So there is a, how can I say? This is a leg of the frontal leg of the dog here. So it's not included in the box, but it is fine. So, well, so this was my program, my implementation of YOLO using Keras. Okay, so the network, what I use has this shape, this structure, and it could be better. The result could be better when we are changing this model. Okay, and right, so bounding box is estimated somehow, but the accuracy of the bounding box is not that much good as we expected, and the accuracy for the sort of the class is very low. And mostly this model estimated the lots of dogs as a Eskimo dog, not the Leonberg. Okay, so there are some problems. Those problems are mainly caused by what I did not implement it. I implemented this, reading XML data and generating data target, and also developed the training network model. So these are what I did, and I implemented this with Keras, but still there are some important features which I did not implement it. So that is the most important thing what I did not implement was the custom loss function. The custom loss function should be different for the outputs, and so here the different weights should be applied. Okay, for example, x and y coordinates and width and height should have different coordinates, and with difference, like when we are calculating the width and height errors losses, then we need to calculate the square root of the difference here. Square root of the we need to calculate the square root for width and height. Then we need to calculate the difference after that. So that is the way of the YOLO. But here we just calculated all the differences for each features, and also we did not give any weights for the class information here, because there are lots of informations for x and y coordinates, and there's small little information of girl, dog, and cat. Okay, there are 4 informations, right? X and y coordinates and width and height, and there are 3. We have 2 information for the 2 types of dogs, and lots of cases they are 0. So you have to set some weights for that. And also, when you're calculating the loss function, we need to ignore the errors when the object exists. The first bit is 0. So if this bit is 0, then we should not calculate the loss for any errors for the information behind it. Okay, so those are very important feature, in my opinion, when you are implementing YOLO, because different types of outputs are mixed together into the one network, but those are not implemented in my explanation and my course. So this is your job to implement this. So please try to implement this and then check whether the network is working well or not. And also one more thing is you can try is when you just try to use the original Google network here, and you may use the exactly same network to the Google Net or Darknet or anything, and then you may just remove the final layer, the final dense layer, and you can add the new layer. You may concatenate, and you can train the final layer only. Then this type of learning is called transfer learning. This is also used for the YOLO implementation of the original paper. So you can try this as well. Okay, this was my last class, and I wish you have enjoyed my class of image processing in this semester, and have a good vacation. Bye bye.